railroad track method. Let's do a conversion. Let's convert 9.3 micrograms per second to 1 pound per year. That sounds like a fun time, doesn't it? And you can see that well enough? I want to get rid of the glare. So the railroad track method is really where you draw a line, and then you're going to put a lot of unit factors in. Unit factors come from unit equations. So maybe the first one we might think about is 1 microgram equals how many grams? 10 to the negative 6. So maybe right here I say I want to get rid of microgram. So I put it down in the denominator because microgram over there is in the numerator. And I'm going to put gram there. Then I tell students always put 1 in front of the metric prefix, and then what you put up here is the metric prefix, 1 times 10 to the negative 6. And now we've dealt with micrograms and we have grams. Now, I probably need something. I hope it's on here. It's not my favorite one. 1 kilogram is equal to 2.205 pounds. I was looking for the unit equation that went from pounds to grams exactly. Maybe this will make it more interesting. Let me make this look like a pound and not a weird H. So it looks like I need kilograms. So I'm going to put a kilogram there. I'm going to put a gram down here. Put 1 in front of the metric prefix, and the metric prefix goes in front of the base unit. Kilo, 10 to the third. I'm going to just write 1,000 grams. All right, now I get to come over here and grab this unit equation as a unit factor and say 2.205 pounds, same thing as 1 kilogram. So we're cruising right along. We've gotten rid of a lot of pesky units maybe. Micrograms went away there, grams went away, kilograms went away. Now I'm in pounds. If I pulled out my calculator right now, I would know pounds per second. Let's work on this second. I want seconds to go away, so I put it up top. How many seconds in a year? Quite a bit. Let's stick with something we know. How many seconds in a minute? All right, that's a good 1 minute. All right. And we could have a unit equation that would say 1 minute, same thing as 60 seconds. Next up, how about 60 minutes in 1 hour? Hopefully I left enough room. 24 hours is equal to what? 1 day. All right, now you can probably tell me how many days in a year, right? And I'm gonna go 365 and a quarter. How do you like that? Why did I do that? Yeah, leap year. So now I pull out my pen and say, let's make sure all these units are doing what they're supposed to. Here's the second. There's the second. This minute, that that hour, that day there. So my units told me when I need to divide by 1,000 grams. Looks like a lot of things are just multiplying everywhere. So then we go 9.3 times 1 to the negative 6, divide by 1,000, multiply by 2.205, times 60 times 24 times 365 and a quarter. So 0.65 pounds per year. How about another railroad track method? So we have a sample of aluminum, and it says it's 10.55, 9.35, 20.88 in centimeters there. That's the dimensions. And what is the mass? So here I see a mass. So that might be a good place to start, maybe. So I have centimeters squared, and if I put this up top like this, one of these might cancel and make this a squared, right? Let me put in another one. And that might cancel and make that just a centimeter. Now I'm going to put in the 20 point. And that's going to cancel that one all the way away. I'm going to go ahead and put this back in like this and tell you that a centimeter times a centimeter times a centimeter equals a centimeter what? Cubed. And that's going to cancel there. So regardless how we think about it, we're going to get the cubes to cancel. And so here we go, 2.70 times 9.35 times 10.55 times 20.88. Looks like we're limited to 3 digits. So there's the mass. A sample of aluminum, which is 9.35 centimeters by 10.55 centimeters by 20.88 centimeters, has a mass of, there it is, we figured it out using density. Let's ask one more question. We kind of didn't do it straight off. So when we do multiplication division, we can't have any more sig figs than the data going into that calculation. The lesser amount of sig figs. Notice I didn't say anything about decimal position. When do we use decimal position? Subtracting addition. Yeah, I heard some things about zeros. Be careful, we're gonna have to go over that again. We'll go over that again. What volume does 5,561.07 grams of aluminum have? So I'm gonna do a short little railroad track here. I'm gonna say, well, this word question, you always like word problems, right? They're the greatest. There's just one number and one unit. I'm gonna put it in the numerator, and then my units will tell me if that's the right spot. And I could even get fancy and say grams of aluminum. And if this was the only question, I'm also given this number here. And I imagine this comes from a unit equation. That might say 1 cubic centimeter of aluminum is the same thing as 2.70 grams of aluminum. And I tell students, always make this look like unit factor. Well, I'm gonna cut to the punchline. So it looks like I'm dividing by density. And I didn't ask myself, am I gonna multiply by density? Am I gonna divide before I started the problem? What I did is I wrote down this number in its units. I looked at density and said, you know, I can get my grams to cancel, and what type of unit am I left with? A unit of volume. So I think it's all set up correctly. As long as I don't make a fat finger error on my calculator, everything should work. 5, 5, 6, 1, 0, divide 2.7. We've answered that question. But now for your amazement, a lot of you on the quiz were very successful when you said, why don't I calculate volume first? So down here, if we said, well, let's just calculate volume first. I'll take that number, multiply it times this number, multiply it times this number, and I'm gonna get centimeters cubed. Here we go, 10.55, multiply 9.35, multiply 20.88. And what is my calculator spitting out at me? 2059 point. And look. Of course, I only know this to 3 digits there. All right, so going back to that original question, once we knew the volume, we could take our volume, multiply it times our density. So here's another railroad track with density going away, or volume canceling away. Here it is. And I actually have a 6-9 here. Here we go. So behold the beauty of the railroad track. Let's go back to the original problem. Here's this aluminum sample. How much does it weigh? Well, if we multiply the 3 sides, we get volume. Once we know the volume times density is mass. All right, then I said, what if you have this mass? What's its volume? We divided by density, got the volume. Or we just plug it all together in one big railroad track. And notice we have the elements of volume. Here's the product of the three sides. That's going to give us volume times density there. That's going to give us the mass. Good question. Any more questions? Now on to something new. When I first moved to this town, the temperature was like 97, 98, and everybody said, oh, it's so hot. And I had moved from Texas, where it's like 105, and I loaded up a Ryder truck and drove up here. I got up here and it's nice, dry heat. It's not hot at all. So the point of that story is sometimes students say temperature is a measure of hot or coldness. And those are real subjective terms. Temperature can be thought of as a measure of kinetic energy or measure of energy, the average kinetic energy or motion or speed of particles in a system. And when you heat up a gas, pressure builds up because the gas molecules start to move around quicker. When molecules move fast, they have more energy than when they move slow. And so temperature that's really what it is measuring, kinetic energy. So first on the list is Fahrenheit, Daniel Fahrenheit. Why does he have a temperature scale named after him? He invented the mercury thermometer. He said, oh, this is neat. Now what do I do with it? So he said, I'll make the coldest thing I can think of, and that's a ice brine bath is the way I read about it once. And you do this when you make homemade ice cream. If you made homemade ice cream with rock salt and ice, nice physics experiment, a chemistry experiment. And he called that 0 degrees Fahrenheit. And then the second part is, to me, the story seems real hokey. His second reference point was his body temperature, and he called that 96 Fahrenheit. Why is that hokey? Yeah, it seemed like maybe you'd call it 100. Does anybody know what normal body temperature is? 90 what? 98. So was he suffering from hypothermia? And then if you go do some research, he originally called it 90, but then he recalibrated his thermometer. Yeah, so the 0 is understandable. Yeah, why wouldn't he just call his body, why not some even number? Why 96? And it was, but that's all I was able to find. And then you've heard of Celsius, also sometimes called centigrade, which is kind of interesting and nice. It makes sense. You've heard of century, centigram. 100 divisions between 0, which is the freezing point of water, and 100 degrees Celsius, which is the boiling part. So there's the centigrade, chopping that up. So here's another interesting thing. Where did the Kelvin come from? The Kelvin scale was proposed by the English physicist William Thomson, who was later knighted and given the title Lord Kelvin. I still have no idea what Kelvin, it's not in his name, Thomson or William. At least we don't have the scale bills. So this will tie back to, I said, temperature is a measure of average kinetic energy. So the Kelvin scale assigns a value of 0 Kelvin to the lowest possible temperature. What is can't you get any colder than 0 degrees Kelvin? This is the theoretical temperature at which atoms would have no motional energy. So even when you have a solid and the atoms are fixed in place, there's still some vibration. They're moving around. 32 degrees out. It was like 13 degrees this morning when I walked my dog, and when I got back, it was 11 Fahrenheit. All right, so there's the 100 degrees between boiling and freezing. So here's this Kelvin scale. 0 degrees Celsius is 273. Notice there's a 100 degree change here. So a 1 degree of Celsius is also a 1 degree on the Kelvin scale. That's interesting and sometimes convenient. And so at 0 Kelvin, we call that absolute zero. Matter ceased to have any kinetic energy at that point. That's negative 273 Celsius and a whopping negative 459 degrees Fahrenheit. How many of you have been to the STEM Center? All right, good, one person. I was down there once and somebody came in and says, what's your favorite example of the usefulness of an equation of a line? You think the equation of a line is useful? And I said, oh, it's this here. I get my Cartesian coordinate system, X and Y, and I'm going to call the X-axis Celsius and the Y-axis Fahrenheit. And I know that water freezes at 0 degrees Celsius, 32 Fahrenheit, and that's a point. And then I come over here 100 degrees on the Celsius scale and go up to 212. That's where it boils. And I got 2 points making a line. So I say Fahrenheit equals the slope, rise over run. It went from 32 to 212 and 0 to 100. So there's my slope. Here's my Celsius temperature plus the y-intercept, 32. And I get my nice y equals mx plus b. There it is. So now if I know the Celsius temperature, I can calculate the Fahrenheit temperature. So for fun, we'll see this on the next page. Now I'm gonna do it just right here. Fahrenheit equals 9/5 degrees Celsius plus 32. What if I need to go the other direction? I'm gonna minus 32 from both sides. All right, now I'm gonna multiply both sides by 5/9. Why don't I write what I just said? All right, here we go. So when I got back from my walk, it was 11 degrees. Let's see what that was in Celsius. 11 minus 32, I'm gonna hit enter, and I'm gonna go times 5, divide 9. It was below freezing. Negative 11.7 degrees Celsius. So here's this thing we just derived. If we want to go from Celsius to Fahrenheit, we're gonna go, I should have left that in, right? What did I just have up there? Anybody take notes? 11.7. My calculator register took my notes for a day. All right, I'm gonna go times 9, divide 5, negative 21 plus 32. So when you need to go from Fahrenheit to Celsius, order of operations is a little different. Take your Fahrenheit, minus 32, multiply by 5, divide by 9. So this Kelvin reading. Unfortunately, if you're in Fahrenheit, you're gonna have to convert to Celsius. Once you're in Celsius, to convert it to Kelvin, we add that 273.15, gets us to Kelvin. That's to go from Celsius to Kelvin. If we're in Kelvin and we need to get to Celsius, we're gonna subtract 270. So random motion of matter. What is matter again? We talked about that the first day. Anything that occupies space and has mass. There's 3 phases of matter. There's actually more, but we're just gonna deal with these 3 in this course. Solid, and a liquid, and a gas. So you pull some butter out of the fridge and you're like, I'm gonna tear up my bread spreading this hard hold stuff on there. So you put it in the microwave and you're absent-minded, so you put the same number that you do your coffee, like 90 minutes or 90 seconds. And as you impart more kinetic energy, it heats up, turns to a liquid, and eventually you could probably turn your butter into a gas. It'd probably be kind of dangerous, like an oil fire type of thing. However, I've put my mug of water in the microwave and you can heat it up till it boils. It turns to a gas. So we want to be able to explain a solid, a liquid, and a gas. Solids, we say, are rigid. The atoms are locked into place. They have no flow. They're incompressible. They have a fixed volume. Both liquids and solids, we say, are in the condensed phase. They're both incompressible. But a liquid, the molecules aren't locked into place. They can move around. That makes it like a liquid. Still have a fixed volume. And we say a liquid takes the shape of its container. You pour water into a container, it takes that shape. Gases, they flow. They can expand indefinitely. They're compressible, so they don't have a fixed shape or a fixed volume. So atoms are a combination of atoms stuck together. We call molecules. We also can call them formula units. For right now, this is a good slide to tell you that everything in the universe is composed of atoms. That's the take-home message with that slide. So speaking of formula units, here is a formula unit of sodium chloride, where the green represents the chloride, those purple represent the sodium. And when we write the chemical formula for sodium chloride, it's NaCl, and that represents the simplest unit. But here, if we had this many atoms, we probably couldn't see it with the human eye, of course. So this looks like a chunk of rock salt, has billions upon trillions of these atoms. Of course, these are special type of atoms in that one has gained electron and one has lost an electron, so we call them ions. But we have this well-ordered cubic arrangement. So this might be a little redundant. In liquid matter, atoms or molecules are close to each other but are free to move around. So that sodium chloride ionic solid kind of locked in place. Liquids have a fixed volume because their atoms and molecules are in close contact. I said solid phase and liquid phase we call the condensed phase. So here's some good examples of liquids. Mercury, a metal that's a liquid at room temperature and pressure, atmospheric pressure. So atomic molecular motion. What is temperature a measure of? Yeah, kinetic motion. So here a solid, they can move around but they're fixed in points. Liquid, they're still locked close to each other but they can move around. Gas, free to move far apart. And this is a good ending point.